sklearnmixture Bayesian-Gaussian mixture. Description: a probabilistic model that assumes the data is generated by a mixture of Gaussian distributions, with the number of components learned automatically. It utilizes a Bayesian approach with a Dirichlet process prior for the number of components, allowing for flexible model selection. Inputs: X, a 2D array of shape n samples, n features, representing the data points, n components, and integer specifying the maximum number of components to consider. The model will automatically determine the optimal number of components within this range based on the data. Outputs: weights, a 1D array of shape n components, representing the mixing weights for each component. Means, a 2D array of shape n components, n features, representing the mean vectors for each component. Covariances, a 3D array of shape n components, n features, representing the covariance matrices for each component. Steps: initialization: the model initializes with a random number of components within the specified range. Expectation maximization (EM) algorithm: the model iteratively alternates between the following steps. A step calculates the posterior probabilities of each data point belonging to each component. M step updates the model parameters weights, means, and covariances to maximize the likelihood of the data given the current component assignments. Bayesian inference: the model uses a Dirichlet process prior to regularize the number of components, preventing overfitting. The prior encourages sparsity in the model, effectively selecting the optimal number of components. Metrics: Bayesian information criterion BICA score used to select the best model based on the trade-off between model complexity and data fit. AKK information criterion AK, another score similar to BIC, used for model selection. Visualization plots: scatter plot visualize the data points colored by their assigned components, highlighting the clustering structure. Density contour plot overlay the density contours of each component on the scatter plot to visualize the distribution of data within each cluster. Fine-tune parameters: n components, the maximum number of components to consider. Weight concentration prior type controls the strength of the prior on the mixing weights, influencing the sparsity of the model. Options include Dirichlet process and Dirichlet distribution. Weight concentration prior, a float specifying the concentration parameter for the Dirichlet prior. Uncertainty methods: predictive distribution: the model can provide uncertainty estimates for new data points by calculating the predictive distribution, which represents the weighted average of the component distributions. Confidence intervals: the model can calculate confidence intervals for the estimated parameters, providing a measure of uncertainty. Challenges and fixes: Challenge 1: choosing the right number of components. Sample use case that resulted in Challenge 1: a data set with a complex underlying structure that may require a large number of components, but overfitting could occur if the number is too high. Fixes to Challenge 1: use the BIC or AK score to guide the selection of the optimal number of components. Explore a range of possible values for n components and compare the model performance using cross-validation. Challenge 2: dealing with high-dimensional data. Sample use case that resulted in Challenge 2: a data set with many features, which can lead to computational difficulties and potential overfitting. Fixes to Challenge 2: use dimensionality reduction techniques such as principal component analysis (PCA) or feature selection methods to reduce the number of features. Consider using a more efficient algorithm for fitting the model, such as the variational Bayes method. Challenge 3: handling data with different scales. Sample use case that resulted in challenge 3, a data set with features having vastly different ranges, which can negatively affect the model's performance. Fixes to challenge 3. Standardize or normalize the data to ensure that all features have a similar scale. Experiment with different covariance structures to accommodate the potential differences in feature scales.